In this question, we're given 4 solutions, or in one case, pure water, and we're asked to rank them in terms of their freezing point and in terms of their boiling point. So the lowest freezing point would be 1, 2 for the next, so on and so forth, and then 4 would be the highest, and then same for the boiling point. So I'm going to talk about the freezing point, and I'm going to go through one example of where we actually find the freezing point depression. And then I'm going to try to explain as best I can a way you can do this without having to do all of the math. But it's a little bit complicated to do it without all of the math. You kind of have to practice at it. So let's start with the freezing point depression formula. Delta T sub F equals I, the Van't Hoff factor, times Kf, the freezing point depression constant, times M, the molality of the solution. So the Van't Hoff factor is how many species the thing breaks up into solution. And the molality is the moles of solute per kilogram of solvent. So in order to find molality, we need molar mass. In order to find I, we need to think about what the solution is. So I'm going to put I here and MM here for molar mass, and the molar mass is going to be in grams per mole. And then that'll help us to solve this. So let's look at this. We have 2.6 grams of Ki in 450 milliliters of water, 2.6 grams of glucose in 450 milliliters of water, 200.6 grams of glycerin in 450 milliliters of water, and 450 milliliters of water. Well, if you're going to dissolve anything in the water, it's going to lower the freezing point. So the one with the highest freezing point, which is going to be 4, is going to be just the pure water. Now let's find all of these things for the other ones. So for Ki, when Ki, because it's ionic, dissolves in solution, it's K plus and I minus. Note that strong acids like HI will also dissociate in solution, but ionic compounds will dissociate, so this is 2. This is a covalent compound, you can tell, because there's no metal. It's all nonmetals. So for covalent compounds, they do not dissociate in water, and this is true of both glucose and glycerin. So I is 1. The next thing we need is the molar mass, because that will help us to find the molality. So the molar mass of potassium iodide is 166.00. The molar mass of glucose is 180.16, and the molar mass of glycerin is 92.09. So now we have the Van't Hoff factors and the molar mass. And I'm going to go through finding the actual freezing point depression for just one of these things with Ki, and then talk a little bit about how you can do this without doing the math. So we need I, Kf, M. Well, for potassium iodide, I is 2, because it breaks up into, again, K plus and A minus. The Kf for water is 1.86 degrees C per M, molal, times the molality. And you'll recall that molality is equal to moles of the solute over kilograms of solvent. And of course we don't know either one of these things. So we need to take our 2.6 grams of Ki times 1 mole of Ki per 166.00 grams of Ki in order to find the molarity of, or the moles, of potassium iodide, which turns out to be 0.01566 moles. And only 2 significant figures, because this is 2. For kilograms of solvent, it's a little bit weird because they don't actually give us the density of water, and without knowing the temperature, we don't necessarily know the density of water. So we're just going to assume that the density is 1. It's very close to 1. At 4 degrees Celsius, it's exactly 1. So it's very close to 1. So we're just going to assume it's 1. So instead of 450 milliliters, we're going to use 450 grams, which we're going to convert to kilograms, which is 0.450 kilograms. So our moles of solute, 0.01566. Our kilograms is 0.450 kilograms. And when you do that math, you find that this is 0.0348 molal. We can now plug that into our delta T equation. So we have 0.0348 molal, 2 times 1.86 times 0.0348, and we get delta T sub F equals, to two significant figures, 0.13 degrees C. So this is the freezing point depression, which means since it's pure water is 0, the actual freezing point is negative 0.13 degrees Celsius. You could repeat that for glucose, and you could repeat that for glycerin. The other way you can do this is a little bit challenging because some of them have different Van Hoff factors than others. Since you have a constant mass of the solute and a constant amount, it is given in milliliters, but we could assume it's grams, mass of water, okay, we can compare these things without actually having to do the math. Essentially, what we would do is the one that's the lightest is going to have the greatest number of moles. However, because this breaks up into two things in solution, instead of using this molar mass, we would actually have to use half of this molar mass, which would be 83.00 grams per mole. And this is a little bit weird, so if you don't want to do it this way, I totally understand. But we can essentially divide this by 2 and get this. Now we can compare them. The one with the lowest molar mass, divided by the Van Hoff factor, is going to be the one that is going to be having the lowest freezing point depression. So it turns out that Ki has the lowest molar mass divided by the Van Hoff factor, which is going to be 1, followed by glycerin, which has a lower molar mass, which is 2, followed by glucose, which is 3. If you don't like this, because it doesn't really make any sense, just solve them all out. It doesn't take that long. You can solve every single one of them out, and you'll actually find which one has the lowest freezing point depression. As far as the boiling point elevation, there, delta TB is I times KB times M. But remember that it's an elevation. So adding solute will increase the boiling point. Said another way, it decreases the freezing point depression, and boiling point elevation, so you get the exact opposite effect. 1 becomes 4, 2 becomes 3, 3 becomes 2, and 4 becomes 1. So whatever you get for the freezing point, you're going to get exactly the opposite for the boiling point.